Hey, so welcome back to the second session of EI 25 this year. And the first panel discussion session will be led by Professor Cecilia Laschi from National University of Singapore. And she is a very experienced moderator of panel discussion sessions. So I'm going to simply hand over this session to you. So maybe you can just start with your own 10 minutes presentation and then followed by other panel members' presentation. Cecilia, thank you very much for joining, and I will hand over to you.
Thank you. Thanks very much to you, actually, for bringing this wonderful conference up every year. So it's becoming a very joyful, very enjoyable tradition. So thanks a lot to you, and thanks to all the other organizers as well, of course. So it's really my pleasure to start up with this panel session today, the first one of the conference. So let me share my slides. I prepared a presentation to raise a few points for discussion. Basically, you see from my title that I want to put up some issues, some discussion about the way we control robots with embodied intelligence. So do we want to control them, or do we want to reduce the control burden to make them work? What I always teach my students, and I say in all my conferences, that what we learn from nature is that, we see complex systems in complex environments, but their behavior is very fast and efficient. And this is exactly what we should copy in robotics. So we should build robots as complex as needed to really behave in a proper way in the real world and addressing a complex real worlds with their own complexity. So all this we can learn from nature if we understand the simplified principles that nature put in place for control and for sensory motor behavior. So this is what Fumi already introduced earlier. So let's say the sense, think, act paradigm that we use widely in robotics. The act part is what interacts with the environment, and the sense part is what receives something from the environment. Don't look at the details inside the diagram, but this is our robot, and there is a plan block, some planner, some intelligence, some brain. So embodied intelligence can be very powerful simplifying principle for robot control, because it introduces the use of external interaction forces from the environment. So it introduces an additional arrow from the environment directly to the body. This is, for me, we were discussing what is embodied intelligence. We want to discuss in this conference. This is, for me, the meaning of embodied intelligence. And why is it a simplifying principle? Because it's like closing a control loop here on the robot body only. So it's like, focusing on only these interactions with the environment. We forget all the rest. This is what we like in embodied intelligence, and we focus on this, and this is also what brings us to soft robotics, because if we want to focus on those two arrows, we want to grasp the simplifying principle of these interaction forces with the environment, then we need a soft body. We need compliance in our body. And this is also a big lesson that we learn from nature. If we look around at the majority of animals, and including human beings, where the body mass is mostly soft. So in my own research, as most of you know already, a wonderful model has been the octopus. It's not just a model for soft robotics, but also for embodied intelligence, because it shows very clearly how many tasks can be simplified by using the interaction with the environment. This is just one of the many examples that we can learn from an octopus. So we Okay, sorry. This is the reaching movement to grasp, you see, an object, and you see that there is a very nice bending which reduces completely the water drag. So this movement is not against the water, but it is helped by the water, by the interaction with the water. And if we look at the biology of it a little bit, we found that the brain of this animal has only to set the 3 parameters, and the rest is done in a very simplified way, thanks to the morphology, the fact that the body is soft, the arm is soft, and the interaction with the water, which helps. So in this project here in Singapore, I'm trying to demonstrate it with some numbers. We want to demonstrate the energy efficiency through some fluid dynamics. We want to model this arm and model the interaction with water, and then, of course, to build a robot. And thanks to this other project, which is a collaboration between Italy and Singapore, we could collaborate with Polytechnic of Milan, who developed a modeling framework for muscle activations. And we can simulate, as you see, the activation of all the muscles in an octopus arm. So what you see in this simulation is one of the many patterns that we tested. This is the best one, which gives a movement very similar to the octopus one. So we found which muscles should be activated and when to obtain the same reaching movement. And as I said, of course, we want to use all this in robotics, and this is a prototype of a robot that can do the same reaching movement. It's also very fast. So what is interesting here is not the movement itself, but is the fact that similarly to the animal, the proximal part, the part that you see before the bending, that part is very stiff, while the rest, the distal part, is completely passive. This is the secret for the animal to be helped by the water instead of fighting it. So all this movement in the animal, there are many muscles, so very complicated control. We have just one actuator, which is a tendon with a motor. So super simple control. This is another possible movement in the octopus, which is the swimming movement. Let me jump to the better part of the video. So we study how we can generate propulsion with an anisotropic stiffness of the arms, and this is how the robot can swim. And here as well, the fluid dynamics is pretty complex to generate propulsion, whatever, but we only have one actuator, one motor. We can have 2 if we want to steer, but 1 is enough for swimming. We also investigated another interesting characteristics of the octopus arm, which we found also in the elephant trunk, as well as in so many structures in nature, including plant structures, which is the logarithmic spiraling. They all follow this mathematical relation. So we built a prototype which has the same, of course, morphology. So it also follows the logarithmic spiraling, and it can produce very similar movements as an elephant trunk. We have data from elephant trunk, so that's why we consider it for comparison. Even if it's completely different in terms of muscle arrangement, here we only have 3 cables, 3 actuators that are 3 cables acting as tendons with their motors. So completely different structure, very similar movements, because we follow the same principle of logarithmic spiraling. Again, 3 actuators only, simplified control. And so since these soft arms are so cool, we can think of applications for them, but you see that even if we start with the idea of reducing control, those applications are introducing the need for control again. Of course, for me, it's very natural to address marine applications for soft robots, but there are also more practical kinds of applications. So this arm was designed for cleaning tasks. And here you see that you cannot see the actuators inside. They are also cables, and we have 4 actuators, and so the number is starting increasing a little bit. And it can actually do very nice thing. It can completely contract this way and it can bend also very nicely, very widely. But again, now we start having some more parameters to control. Biomedical applications of soft robotics are also increasing. They increased a lot in the last decade, and there are really many different areas where soft robots can be used in medicine, the biomedical field. One of them is personal care, caregiving, assistance to the elderly, for example, which is a priority also here in Singapore. So we are addressing assistive soft robotics. This is the concept of an arm for helping the elderly people to stand up from sitting or transfer from a chair to another. So we developed arms, soft arms for this. They have anisotropic stiffness as well. Actually, inside this module, there is a part which is also inspired by from the octopus, and it's confidential because we are patenting. In this case, also we have some more actuators. We have 2 actuators per arm, again implemented with tendons and motor. In a previous project in Europe, a European project I support, we designed this other arm, which is for bathing tasks, for showering. So in this case, you see there are 2 modules, and each of them has 3 pneumatic chambers and 3 tendons with motors. So again, the number of actuators is increasing, and the number of control parameters is increasing. But in tasks like this, we really want to control precisely the end effector and not only the end effector. So that's why the applications are introducing back the need for control that we wanted to simplify with soft robotics and with embodied intelligence. So what's the issue with soft robot control? The traditional approach is using models of the transformation between the actuator space, whatever the actuators are, and the task space, so the end effector position. And of course, we can apply this approach to soft robots, this model-based approach, but do we have models? What does it mean to have models of soft robots with embodied intelligence? We said that embodied intelligence is especially in this double arrow of interaction with the environment. So it's not enough to have models of the internal interactions, which is what is typical in robotics, like understanding and modeling the effect of actuators on the robot movement, so the robot deformations in our case. We also need to model the external interactions to some extent, as we have seen before. So we proposed this approach actually a couple of years ago, proposing to use one equation. This is a very general equation, but the message is that it has to contain both the internal interactions and the external interactions. And we also reviewed the existing techniques, because there are techniques for both cases, either in the continuum mechanics realms or with some parameterization. And of course, there are also techniques based, data-driven method to solve those modeling problems. And so we have the models. We can do some model-based control, but we have another option, which is to replace completely the controller with learning, with a neural network, for example. And this is an approach that is being used. We generate directly those relations, and we can probably better cope with dynamic tasks, with tasks like those assistive tasks where we want to control not only the position but also the force, if the soft robot allows to do that, or we may wish to control full body position in this case. And this is actually growing field. We know that the number of publications of robotics is growing, but it is also growing the number of publications addressing control problems, and among them those addressing learning-based control. So this is one direction that our community is taking. but there is also a direction which is an opposite direction that we can only also take. So what about removing control completely? I mean, the electronic part of control. So what about electronics-free robots? So we don't have any actuators to control in the traditional way. So in this example, we actually replace whatever is controlled, like the valve controlling the actuators in these fluidic robots with what bistable mechanism. So this bistable mechanism can actually oscillate between its two stable states and oscillating between the two with just one constant input, which is the pressure. It acts as an oscillator. And oscillators can do very interesting things like all the rhythmic movements. In this example here, we add a switch, which is a mechanical switch. So the two states are changed when there is a mechanical stimulus, for example, contact. And then the system goes in the second state, which is where the fingers of this gripper are actuated and they can grasp an object. But as I said, we can produce all the rhythmic movement with a bit more complex fluidic circuitry. And with these rhythmic movements, we can control actuators and all the rhythmic possible, for example, locomotion patterns, walking or swimming. So I'm going to my conclusions, which is pretty simple. We had to decide the direction we want to go, starting from embodied intelligence, and we need to find a balance. So maybe we should put the embodied intelligence back into the full picture, and we should consider all the different levels of control that are possible. And as I said, just finding a balance between the two extremes where we have zero control, we have full control in the traditional way, and we have intermediate levels of control that is simplified by embodied intelligence. So thank you. Let me thank all the guys in my group who do these wonderful works and the funding agencies, of course. There is also a small announcement for those of you working in soft robotics and teaching soft robotics. There will be textbooks available soon. And very last announcement, if you are interested in those topics and more, we are also hiring here at NUS. So thank you. And I stop sharing here.